what SAST catches versus misses. Now, here's something that separates someone who's genuinely learned SAST from someone who's just memorized the term. SAST has real limits, and knowing those limits is just as important as knowing what it catches. Let's go back to an example we covered in an earlier video, the Ebola vulnerability, where an API returns someone else's order simply because nobody checked if the requester actually owns that order. Now ask yourself, would a tool like Semgrep catch that bug? Let's look at the actual code. It's a clean, simple function. It takes an order ID and returns that order. There's no raw SQL string. There's no hard-coded password. Syntactically, this code looks completely normal and safe. A static analysis tool scanning this file will very likely say, "No issues found." But we already know from understanding the actual business logic that this code is seriously flawed. It never checks whether the order being requested actually belongs to the person requesting it. The problem isn't in how the code is written. The problem is in what the code forgot to ask. This is the core limitation of SAST that every AppSec professional needs to understand. Static analysis tools are excellent at recognizing patterns that are risky no matter what the application does, but they have no understanding of your specific application's business rules, like users should only see their own orders. That kind of logic flow requires either a human reviewer who understands the system, or a different category of tool entirely, which is exactly what we're covering next. In the real world, SAST tools typically run automatically on every single code commit as part of a CI/CD pipeline, catching the patterns it's good at catching immediately and consistently, but a mature security program never treats SAST as the entire security review. It's one strong layer in a much larger system. What SAST catches versus misses. Now, here's something that separates someone who's genuinely learned SAST from someone who's just memorized the term. SAST has real limits, and knowing those limits is just as important as knowing what it catches. Let's go back to an example we covered in an earlier video, the Ebola vulnerability, where an API returns someone else's order simply because nobody checked if the requester actually owns that order. Now ask yourself, would a tool like Semgrep catch that bug? Let's look at the actual code. It's a clean, simple function. It takes an order ID and returns that order. There's no raw SQL string. There's no hard-coded password. Syntactically, this code looks completely normal and safe. A static analysis tool scanning this file will very likely say, "No issues found." But we already know from understanding the actual business logic that this code is seriously flawed. It never checks whether the order being requested actually belongs to the person requesting it. The problem isn't in how the code is written. The problem is in what the code forgot to ask. This is the core limitation of SAST that every AppSec professional needs to understand. Static analysis tools are excellent at recognizing patterns that are risky no matter what the application does, but they have no understanding of your specific application's business rules, like users should only see their own orders. That kind of logic flow requires either a human reviewer who understands the system, or a different category of tool entirely, which is exactly what we're covering next. In the real world, SAST tools typically run automatically on every single code commit as part of a CI/CD pipeline, catching the patterns it's good at catching immediately and consistently, but a mature security program never treats SAST as the entire security review. It's one strong layer in a much larger system. DAST, Dynamic Application Security Testing. Now let's cover DAST, Dynamic Application Security Testing, and you're going to notice immediately how differently this tool approaches the exact same problem. Where SAST reads your code like a manuscript, DAST does something completely different. It actually attacks your application while it's running, the same way a real attacker would, sending genuine requests and watching how the live system responds. Let's walk through what a tool like OWASP ZAP, which is free and one of the most widely used DAST tools in the industry, actually does in practice. ZAP doesn't read a single line of your source code. It doesn't even know what programming language your application is written in. Instead, it sends real HTTP requests directly to your running application. A normal request first to see typical behavior, and then a series of deliberately unusual ones, adding strange characters to a URL, trying negative numbers where a positive ID is expected, attempting classic injection patterns. Then, critically, it watches and records exactly how the server responds to each one, looking for errors, unexpected data leaking out, or any sign that something behaved differently than it should have. If you're ever asked to explain DST in an interview, here's a clear, confident way to put it. DST tests a live, running application from the outside, the same way an actual attacker would approach it, sending real traffic and observing real responses, rather than reading source code from the inside. DST versus SAST. This naturally raises an important question. If SAST already scans your code, why do you also need DAST? Let's answer that directly using the exact same Bola example from before, because it makes the difference crystal clear. Remember, SAST looked at that order retrieval code and said no issues found, because nothing about the code's syntax looked dangerous. Now watch what happens when DST examines the exact same feature instead. DST doesn't read the code at all. It doesn't even have access to it in many setups. Instead, it does something much simpler and, in this specific case, far more effective. It logs in as one test user, then deliberately requests another test user's order ID, and simply checks, did the server hand over data it shouldn't have? If the answer is yes, DST just found a real, working Bola vulnerability, not by understanding the code's logic the way a human reviewer would, but by literally attempting the exact attack a real adversary would try, and observing that it actually succeeded. This is precisely why mature security programs run both tools together, rather than choosing one over the other. A simple way to remember the distinction. SAST is like carefully reviewing a building's blueprint for structural mistakes before it's built. DST is like actually trying every door and window on the finished building to see which ones are unexpectedly unlocked. A flaw might be invisible on the blueprint but immediately obvious the moment someone actually tries the door, and that's exactly the kind of gap DST is built to close. In a typical pipeline, DST usually runs a bit later than SAST, often against a test or staging environment. After the application is actually deployed somewhere, it can be tested live. SCA, Software Composition Analysis. Let's move to our third tool category, SCA, Software Composition Analysis, and this one addresses a risk that a lot of developers don't think about nearly enough: the code you didn't write yourself. Here's the reality of almost any modern application. It's built on top of hundreds of open-source packages that someone else wrote, packages you simply installed and now depend on. You might have personally written a relatively small percentage of your application's total code. The rest is borrowed, reused, and trusted. SCA tools exist specifically to check those borrowed packages against a continuously updated database of known security vulnerabilities. A simple, accessible example almost any JavaScript developer has access to right now is npm audit, a free built-in command. Picture running it against a typical project, and it reports back something like, found 3 vulnerabilities, one of them, a popular utility library, has a known high-severity flaw called prototype pollution, with a fix already available. Here's the part worth sitting with for a moment. You never personally wrote a single line of that utility library's code. You simply installed it because it was useful. But the moment it became part of your application, its vulnerabilities became your vulnerabilities too, fully inherited, regardless of who originally wrote that code. If asked to explain SCA simply, it's the practice of scanning every third-party package your application depends on against a known vulnerability database, because your application's actual security surface includes every single piece of code it runs, not just the code you personally typed. Why dependency risk spreads? Let's go one level deeper into why this particular category of risk has become such a significant industry-wide concern in recent years, because the scale of it is genuinely surprising the first time you really see it laid out. When you install a single package, say one helpful utility library, that package very often quietly installs dozens of additional packages underneath it automatically, packages it depends on internally, which you never explicitly chose or directly reviewed yourself. If even one of those 40 or so hidden, secondary dependencies contains a known security flaw, that flaw is now fully present inside your application too, despite the fact that you may never have even known that specific package existed in your project at all. This isn't a hypothetical, abstract concern either. A real-world example many in the industry still reference directly is Log4Shell, a critical vulnerability discovered in a widely used logging library that was quietly embedded inside an enormous number of applications worldwide, ultimately affecting millions of systems virtually overnight, the moment the vulnerability became public knowledge. In real-world AppSec and DevSecOps work, SCA scans typically run continuously, not just once at the very start of a project, but every single time a dependency gets updated, precisely because new vulnerabilities in existing, already installed packages get discovered and publicly disclosed constantly, on an ongoing basis. A package that was perfectly safe yesterday can become a documented, known risk literally overnight, without a single line of your own application code ever changing at all. Building a real DevSecOps pipeline. Now let's bring everything from this video together into one practical, hands-on exercise, because understanding these tools conceptually is genuinely useful, but actually wiring one into a real, working pipeline is what turns "I know what SAST is" into "I've actually built this." Here's the goal, stated simply. Make a security scan run completely automatically. Every single time code gets pushed to a repository, with absolutely no manual step required, and no human needing to remember to run anything by hand. This is done using something called a GitHub Actions workflow file. A simple text file that lives directly inside your project's repository and tells GitHub exactly what to automatically do whenever specific events happen, like a new code push. Looking at the actual example on screen. This file is named security.yml, and it defines one job called scan that runs on a fresh virtual machine every single time. That job does two concrete things. It installs and runs Semgrep, the SAST tool we covered earlier in this video, directly against the entire codebase, and it also runs npm audit, the SCA tool we just discussed, checking every dependency for known vulnerabilities. Here's genuinely good, practical news if you're newer to this. This is a remarkably short file, well under 20 lines of actual configuration, yet it represents real, demonstrable, hands-on DevSecOps work. If you build and commit something like this yourself, even against a small personal project, you now have a completely real, working example you can show in an interview, or simply link directly in your resume or portfolio. Why this one file matters so much. Let's close this video by talking about why this one small configuration file genuinely matters so much more than its short length might initially suggest. In real DevSecOps roles, this is quite literally core everyday work, taking exactly the kinds of security tools we've covered throughout this video, and wiring them directly into the existing development workflows that teams already use daily, rather than treating security as some separate, occasional bolt-on activity that happens only once in a while. Think carefully about the meaningful shift this single file actually represents. Before a file like this exists in a project, security checking typically depends entirely on a human remembering to manually run a scan, which, realistically, under real deadline pressure, often simply doesn't happen consistently or happens unevenly across a team. After a file like this exists, security checking becomes fully automatic. It runs on every single push, completely without exception, and no individual person can simply forget to do it, because the responsibility no longer rests on memory at all. That shift from security as a manual, occasionally skipped step to security as an automatic, inseparable part of the pipeline itself is genuinely the entire philosophy behind DevSecOps as a discipline. If you're ever asked in an interview to describe hands-on security experience, being able to say, "I built an automated pipeline that runs static analysis and dependency scanning on every code push," and actually showing the real file is a substantially stronger, more credible answer than simply listing tool names you've only read about.